Now we look at the radial equation that we got from applying separation of variables to Laplace's equation on the disk. And so it was this differential equation right here, which is actually a Cauchy-Euler equation. And we just found out that the spectrum is n squared, so I can replace that part of the equation. And so this is what we're going to be looking for here. So like I said, this is a Cauchy-Euler equation. And so that means that we are going to look for solutions of the form r to the m. And so substituting this one into the PDE leads us to the characteristic equation m minus 1 coming from the two derivatives plus m coming from the first derivative minus n squared equals 0. So that's the characteristic equation for this particular problem. And so we have m squared minus n squared equals 0, simplifying somewhat. So m equals positive or negative n. And so what we find then is our solution looks like a r to the n plus b r to the minus n. But then we want something that's bounded at 0. And so this is, we rule this one out because it is not bounded at 0. And let's see, so okay, then we also need to check when lambda is equal to 0. And so for the lambda equals 0 case, we have r squared y double prime plus r y prime equals 0. And let's see, so that's same thing as r v prime plus v equals 0 for v equal y prime, and then canceling an r. And so this gives us a separable equation. So if I subtract the v to the other side and then divide both sides by v, I end up with dv over v equals minus dr over r. And then I can integrate each of those, and I get log v equals minus log r plus a constant. And then I'll do the usual thing and put the exponent inside the logarithm, and then exponentiate both sides and get v equals c e to the log r, which just becomes r. 1 over r. And then integrate v to get back my function y. So that will be c1, and then the integral of 1 over r is log r plus c2. And so again, we can use the fact that we want a solution which is bounded at 0 to kick this one out. So that one's gone. So we just get a constant. Okay, so putting this together with what we've found already, we know that we've got a u0, which is just a constant, and it's convenient to normalize it with a 1/2. And then for the positive values of integer n, we have a solution that looks like, so multiplying together the two things we got the radial part right here, and then we got the periodic part right here. And so we can use superposition to throw all these things together, and we have the sum n equals 1 to infinity of r to the n a(n) cosine n theta plus b(n) sine n theta. Whoops, missed my parenthesis there. There we go. And so using now the initial condition, f of theta is u r theta equal to a naught over 2 plus the sum 1 to infinity of, and then we've just evaluated, so there's a capital Rn. And so then from that we can see that the corresponding coefficients for this expansion, those are going to be 1 over pi r to the n integral from 0 to 2 pi of our initial condition f times cosine n theta d theta. And for the sine coefficients, those are pretty much identical.